Hello everyone, and welcome to this next video in the series looking at HL questions from past papers. Today's question is all about complex numbers, and it comes to us from these sections of the syllabus. We've got a little bit of work with complex numbers, their modulus argument form, and we're also directed to use the compound angle formulae. They come from a slightly different section. I've chopped the number off there, but that's from part 3 of the syllabus, geometry and trigonometry. Now, I was tempted to give this one 2 stars because I don't think it's that tricky if you spot what's going on, but I'm going to leave it at 3 because I think if you, I don't know, it's perhaps easy to get wrong with this question if you're not careful. So having a look, we can see we're given these 2 complex numbers, Z1 and Z2, and we're asked to use the compound angle identities to determine an expression for the following in polar form. Now, they're given in polar form, that's modulus argument form, same thing really. Now, if you know your complex numbers, you probably already know an expression for these things because you've done lots of this and you've learned to generalize results. But the question actually specifies that we have to use the compound angle identity. So really what we're going to do is derive the result that we perhaps sometimes use in class. You may have seen this done already, in which case it's actually quite an easy exercise. But if you haven't seen this done, the language and things used could be a little bit confusing here. And then in part B, hence determine an expression in terms of the arguments for these things. So really this is understanding the modulus argument form of complex numbers, and there's a little bit of tricky algebra. So let's have a look. First off, we're going to want to have a look at our 2 complex numbers. They're given in just generalized forms. We've got the modulus, the moduli R1 and R2, and we've got the arguments theta and beta. Now, if we're going to use the compound angle identities, I've gone ahead and grabbed these from the formula booklet here, and obviously we're going to need to use some of those. So first off, let's just do the multiplication. Let's just go ahead and multiply Z1 times Z2. So that is R1 cos theta plus I sine theta, multiplied by R2 cos theta, cos beta plus I sine beta. So these are just the standard modulus argument forms. Now, you can save yourself a bit of work here by being a little bit canny with how you write this out. So first off, I'm going to get R1, R2 outside the bracket. We know that's where moduluses normally sit. So I'm just going to pop those there. And when you multiply complex numbers before, you realize, hopefully, this follows the pretty classic binomial expansion. So think about squaring a bracket. We're going to have the first term will be real, the last term will be real, and then the 2 middle terms will be imaginary. So what I'm going to do is I'm going to look at the first term and the last term together. So I'm going to get cos theta times cos beta. That's if we're going to follow sort of FOIL here, that would be the firsts. I'm going to skip over outsides and insides and go straight to lasts, and I'm going to have I sine theta times I sine theta. Now the i's are going to multiply together and give me a negative here, so I'm going to get minus sine theta sine beta. So that's the real part taken care of. I'm now going to deal with the complex parts, which are going to be multiplied by I. So I'm going to open a bracket after my I, and then I'm going to end up with sine theta times cos beta. That's the insides, if you like. And I'm also going to have cos theta times sine beta, and that's the outsides. So the trick here is really we've got cosines and sines, we've got thetas and betas, and it's just being systematic that way, making sure we get everything right. So I've followed FOIL, first outsides, insides, lasts, but I've just changed the order a little bit so that I get my real terms together here and my imaginary terms together there. That's always a good idea when working with complex numbers, because that's the idea of the Argand plane, is that we split those separately. Then, as directed, we're going to use the compound angle identities. Now we can see here we've got something here that looks very much like this one, and we've got something here which looks very much like this one. You notice that for the sine compound angle identities, the terms differ, so it's sine A cos B, and then for the cosine ones it's cos A cos B, so that's where they match. You've got to be a little careful reading from your formula booklet here. The middle sign is where it's at, so this one here is a negative. We're going to match that up here to this negative, which is on top, so we take the positive that's here. So I'm going to rewrite this, R1, R2 just stays where it is, and this whole first two terms I'm going to replace with cosine of theta plus beta. There we go. And next I'm just going to leave my eye and I'm going to again look carefully. It's all about this middle sign. This is a plus, which is the top symbol here, and we've got the top symbol from here. So I want sine theta plus beta, which is great because they match, meaning that I can now, well, I don't need to rewrite this, perhaps it's actually already in modulus argument form. Our modulus here is given by R1, R2, and our argument is given by theta plus beta. Now, that, again, that's a result we know from working with complex numbers. When you multiply them, you multiply their moduli and you add their arguments. But this question is actually basically asking us to derive that result. So there's the first part, not too tricky if we pay close attention to the symbols used here. On to the next section. This is going to be very, very similar. It just is division instead of multiplication. It's a little bit harder, but let's go ahead and start writing this one out. R1 cos theta plus I sine theta over R2 cos beta plus I sine beta. Now, again, from thinking about previous work we've done with complex numbers, we are going to want to make this real on the bottom, and the way to do that is to multiply top and bottom by the complex conjugate. So I'm going to want to multiply by R2 times cos beta minus I sine beta. This is a common result and a common technique when we're working with complex numbers, and it's going to eliminate the i's, the imaginary part of the number on the bottom, and lead to something that I can simplify because the bottom will be real. So on the top we're just multiplying by the same thing because this then doesn't change the value of what I have. And let's have a look. This is going to get a little bit messy, but I notice that the top here is going to be very, very similar to what I did on the previous page. The only difference being that I've got negative I sine beta as part of the second bracket. So it's going to look very similar. We're going to have R1, R2. Again, let's get those real parts out front. Cos theta, cos beta. This time it's going to be minus sine theta, sine beta. So the, oh no, let me get that right. The two i's have multiplied to give me -1, but I've also got a negative I sine beta, so that's going to be positive where before it was negative. So that is the real parts, and then I need the imaginary parts. Just sort of going to get a little bit scrunched up here, but let's go for it. Sine theta cosine beta, and this time it is minus cosine theta sine beta. Just squeezing that one up there. Perhaps I should have taken a little bit more space. Then on the bottom I'm going to have R1, R2 again, and here's where that nice conjugation happens, where I'm multiplying by the conjugate, and we should turn everything into real. So the first part we're going to get cos beta times, oh hang on, this is not R1, R2 of course, this is R2 squared, and we've got cosine beta squared. We have got then I sine beta squared, but negative version of that, so we get plus sine squared beta. Then we're going to have the two imaginary terms are going to cancel each other out, so I'm going to have plus I cos beta sine beta, and then I'm going to have minus I sine beta cos beta. These two terms will cancel each other out, and if we tidy up we're going to be left with R1, R2, Now at the top we can look again at using the compound angle formulas. We're just going to see the opposite of what we saw before, which was I've got cosine, cosine, sine, sine. So this section, the middle sign is positive, so I want the lower of these two, so it's going to be cos alpha minus beta. So cos, or in this case, sorry, theta minus beta. I really wish they'd have used alpha. And the imaginary part is going to be, well, again, we've got sine, cosine, sine, cosine, so it's going to be sines, and the middle sign this time is negative. Again, that's the lower, so I've got sine alpha minus, theta minus beta. So this all looks kind of quite complicated, but actually when you see the structure, every term is corresponding to something in the compound angle identities, and it should be matching. So if it doesn't match, you probably know you've gone and made a little mistake with the sign. But there we go. And then on the bottom, this actually tidies really nicely. We've got r2 squared and cosine beta squared plus sine beta squared, or sine squared beta, which is just going to give me 1. So the simplification is quite easy. We cancel one of the r2s, and we're going to be left with r1 over r2 as our modulus, and our argument this time is theta minus beta. Again, that's what we expect. We've seen this result before. When we divide two complex numbers, we divide their moduli and subtract their arguments. But this question again is asking us to derive that result. So I might just tidy that up with one more line. r1 over r2 cos theta minus beta plus I sine theta minus beta. Again, I'm just running out a little bit of space. But there we go. That's that first part done. It's not too tricky, particularly because you should have seen this derivation before. So some nice marks to be gained there. You just need to make sure you do obey the question and use the compound angle identities. When it gives you that kind of advice in a question, it's not just giving you a hint for how you might answer the question. It's telling you have to use those identities. So those should be clearly used in your work somewhere, and you can see how I've gone from here to here using the compound angle identities. The last part really is just tidying up. We can see that part B just says hence, again using the result we've just derived, determine an expression in terms of argument of Z1 and argument of Z2 for argument of the product. Well, the product Z1, Z2, if we just go back and have a look, what we ended up, of course, was the argument was the addition of the angles involved. So here, the argument of Z1, Z2 is just going to be argument of Z1 plus the argument of Z2. And for part 2, the argument of Z1 over Z2 is going to be the argument of Z1 minus the argument of Z2. So quite a nice question this time, just really getting us to derive a result that we should have seen derived already. And if you spot that, there's no reason you shouldn't be getting full marks here. So there we go. Thanks very much for listening again. Have a good day.